Okay, so today we will look at what is known as the spectral radiosity formulation, a slightly advanced topic, but since it is a graduate level course I thought we will do that. So it will take 1 hour for us to discuss briefly this concept and then work out a problem. So far our analysis of enclosures, right, where we try to do enclosure analysis with radiosity irradiation method was restricted to enclosures which were having gray diffuse surfaces. But if you remember, before we started with view factors we spent so much of time in trying to define spectral, directional emissivity, hemispherical total hemispherical spectral emissivity, directional total emissivity, hemispherical total emissivity and so on. We also discussed that there are several surfaces which can exhibit non-gray behavior, that is epsilon lambda need not be epsilon lambda will in general be a function of lambda. We can't we do not have to automatically cut out by saying that epsilon lambda is not a function of lambda, so everything is gray and diffuse. But please remember that this gray diffuse is a good approximation, but there are applications where this gray approximation does not work. The diffuse approximation also does not work, but we are not going to worry about the angular dependence, that is more involved. So if the gray assumption does not work, how do we go about handling the radiosity? Please remember, for the radiosity we simply used radiosity is emission plus reflection, and for the emission we straight away used epsilon sigma t to the power of 4. For the reflection we put rho of that surface multiplied by whatever irradiation is coming on that surface. The irradiation coming on the surface is a consequence of the radiosity from the other surfaces multiplied by the corresponding view factors, and then we worked out all the algebra and we worked out different expressions for getting the q in terms of g, in terms of j, in terms of j minus g and so on. Now for a moment if you think, if you pause and think, if you cannot use that epsilon sigma t to the power of 4 because epsilon lambda is a function of lambda, how do you think the formulation will get changed? Epsilon lambda is a function of lambda, so I just cannot use epsilon sigma t to the power of 4 and have one radiosity. So we have to use, so Deepak is coming out with some answers, he is saying that we have to use the f function chart, right. So if you have to use the f function chart, that means you have to use the f function charts for different ranges of the interval. Are you getting the point? If lambda is equal to 0 to infinity, if there is a value of epsilon 1 for 0 to 3 micrometer, then you will use some f function chart and find out what is the total amount of radiation in terms of sigma t to the power of 4, how much of sigma t to the power of 4, then 4 micrometer to 7 micrometer, 7 micrometer to 9 micrometer, whatever up to infinity. Therefore necessarily you will have to introduce what is called a spectral radiosity, whose units will be watts per meter square per micrometer. Therefore in a wavelength interval d lambda you have to multiply this j lambda multiplied by d lambda, correct, and then are you getting the point, so that you are able to find out so many watts per meter square in that portion of the interval and so on, okay, and then you will have to do a sum over all these intervals to get your final answer. We will go through the rigorous mathematical formulation, but the whole point is it is going to be computationally very expensive if the epsilon lambda versus lambda is very painful, correct, it is going to be computationally very expensive. That is, if your d lambda has to be necessarily very small, then you will have so many spectral radiosities for each surface. If you have a n surface enclosure, you will have, previously you had n radiosities, for each surface you will have m radiosities corresponding to how many intervals you are dividing epsilon lambda. Are you getting the point? Therefore it will be computationally very challenging, okay. There are some approximations, there are some approximate ways of doing this, so we will do this in today's class. So we now look at what is called the radiosity irradiation method needs to be modified Okay. How? Correct. So, the need is established. How? By using a formulation called the spectral radiosity formulation. So, what are the key features? What are the key features of this spectral radiosity formulation? First, epsilon lambda is a function of lambda. Good. First, epsilon lambda, and needless to say, this f is known to us, otherwise we cannot proceed, right. So, then it is an inverse problem. Okay. So, epsilon lambda is a function of lambda. I know what this f is. Now, instead of j, watch here, instead of j, it is j lambda d lambda, which is the net radiation leaving a surface in a wavelength interval d lambda about lambda. Okay. What should be the units of j lambda? Watts per meter square per micrometer. Okay, j lambda will have the units of so that when watts per meter square per micrometer is multiplied by micrometer, you will get watts per meter square, which is the original unit for radiosity. Okay. Now, net spectral so net spectral radiant heat transfer is q lambda. What should be the units of q lambda? Watt per micrometer, very good. So, if I put small q, it is different story, it is watts per meter square per micrometer. Since the whole wavelength interval lambda is equal to 0 to lambda is equal to infinity is not used, I come again, since the whole wavelength interval lambda is equal to 0 to lambda is equal to infinity is not used, we are considering d lambda about lambda, we cannot use the Stefan Boltzmann's law. But does it mean that we cannot proceed with the calculations? Instead of the Stefan Boltzmann's law, what will you use? What is the original law? Which let we will use the Planck's law, right? We use Planck, we use did we use 2 pi C1 or C1 straight away for E? We multiplied that by 2 pi directly C1? Yeah, please check. No, I am not talking about IB lambda. I hope you have not forgotten the difference. Quiz is coming up, right, between the EB lambda and IB lambda. Lambda 2, of course. Correct. don't ask me, sir, why are you using EB lambda, it is not a black body, anyway epsilon lambda will come, don't worry about that. Vikram, any problem? Oh, there is a big story, no? Pi, yeah? Was it pi or 2 pi? No, no, it depends on how I have defined in the earlier classes. If you all say it is pi, huh? Okay, then it is pi C1, huh? It depends on how we have done it, okay, fine. And now Ji, yeah, please watch this. So the Ji will be lambda equal to 0 to infinity j lambda d lambda. Sure, I want to put it j lambda I, yeah. If you don't like j lambda I, you can use j I lambda, it does not matter. Lambda and I must come, lambda is a spectral and I is the ith surface. We just want to leave it as j lambda because we are talking about radiation heat transfer in a n surface enclosure, okay. So this makes it the spectral radiosity formulation, correct, it is a spectral radiosity. If you want to get the total radiosity which we have defined earlier, it has to be done. Similarly Qi, lambda equal to 0 to infinity q lambda I d lambda. Fine. So this is for getting the radiosities. What about view factors, will they change? No. So let's write that all, no changes in view factor calculation. So no changes in view factor calculations. So how do you get the reflectivity? It is spectrally dependent. Therefore you have to invoke Kirchhoff's law. To get the reflectivity you have to invoke Kirchhoff's law and say that alpha lambda is equal to epsilon lambda, okay. So this completes the formulation, this gives you the broad framework after going through this important rules, right. This is like COT or prerequisites. Once we have all this, then we write the formulation. I will write the original radiosity equation which we have been using in the last few classes, and the spectral radiosity formulation equations, and then see this integral lambda equal to 0 to infinity. As engineers, sometimes integral is replaced by summation. If it has to be replaced by summation, so I will have an approximate epsilon lambda versus lambda instead of you having a stupid curve. So that is an approximation is introduced there, that we will see, it is called the band approximation. We will introduce that band approximation and see how to solve this problem, okay. So the problem, suppose if I have a 3 surface enclosure and each surface I will give you epsilon 1, epsilon 2, epsilon 3 for 3 different regions of lambda, you are sunk, okay. So you will calculate all this for the first 0 to lambda 1, then you will calculate for lambda 1 to lambda 2, then lambda 3 to infinity and so on, then finally you can add up all the radiosity, add up all the Q, that is a linear addition will work, okay. Now I think quite a few of you must have got an idea of how the eventual equations will look like, but we will write out the formulation, we will solve a problem, then everything will become clear. We will just take the simple parallel plate formula, but now epsilon 1 and epsilon 2 are functions of lambda. I will just give a simple step function, okay. Now shall we write the, and then most importantly, since I am using this and then I am telling you that epsilon lambda is a function of lambda, in various wavelength intervals I have to use what? I have to use F charts. Okay, so this is the background required for a spectral radiosity formulation. Okay, so we will write the spectral radiosity equation. So, for hemispherical total quantities, what was the original radiosity? We will first write the whatever we are familiar with, and then we will write then Ji equal to epsilon I sigma one. We know this. Yeah. They look similar. Or? J equal to 1. Okay. Now, the spectral radiosity formulation, watch this very carefully. I will write it with orange chalk. Please see whether it is all right. If you do not like this notation, yeah, no, it is fine, it is fine, the notation is good. So the J lambda I is epsilon lambda E B lambda I can't put sigma t to the power of 4 because this is J lambda, this is not J from 0 to infinity. So I have to put epsilon lambda this plus 1 minus epsilon, view factor is the same, and J lambda of J. Okay. For an n surface enclosure, we will have n such equations for every wavelength lambda, and for every wavelength lambda the n equations can be simultaneously solved to get J lambda. Once you get that J lambda, you can integrate it to get Ji. Then you can similarly get Ja for all the surfaces, and Ji minus Gi is the Qi. Is that okay? So what is the additional labor involved? You have to do all that. You have to first get the view factors and all that, write out the radiosity equations, but radiosity equations have to be written for each and every wavelength. But the wavelengths and the surfaces are not coupled. That means for every wavelength you can independently solve. Okay, are you getting the point? For every wavelength range, you can take the n surface enclosure and solve the spectral radiosity equations independently. You don't have to solve the n equations for m number of wavelength intervals simultaneously. Okay, you can solve from 0 to 3 micrometer, get all the values of J lambdas, 3 to 5 micrometer, 5 to 8 micrometer, 8 micrometer to infinity. Okay, so J1 itself, if one is the first surface is 1, let us say we can use superscript 4 wavelength intervals 1, 2, 3, 4. Then you will have J11 plus J12 plus J13. Are you getting the point? All these refer to the wavelength bands. Okay, so now we will write the formulation completely. these can be solved to get j lambda i's. Now okay. So, the q will be q lambda I will be epsilon lambda I by 1 minus epsilon lambda I into E b lambda of I minus j lambda I. What is that E b lambda I? Will be the f function in that wavelength interval multiplied by sigma t to the power of 4, only that much. That E b lambda I will become sigma t to the power of 4 if the j lambda is replaced by one general j which we used in the previous classes, correct? Yeah. What is the key point here? What is the key point here? Algebraic radiosity equations are coupled with respect to come on, algebraic radiosity equations are coupled with each other with respect to what is that? Algebraic radiosity equations are coupled with respect to the surfaces, with respect to the surfaces. Decoupled with respect to that means if in n surface equation you will do the same procedure as what you did before, but you have the luxury of doing it wavelength interval after wavelength interval, okay. So we can carry out, so you can carry out all these calculations sequentially over various lambdas. Therefore, if the epsilon lambda versus lambda is such that no approximation is possible, that you will have to necessarily divide it into 100 wavelength intervals, 200, 300 wavelength intervals, it is computationally very costly. Spectral calculations are very costly. Do not think that only CFD is time consuming. You come to radiation, we will show you on Cray CX1 we have, I can put some radiation solver and I can make the whole CX1 struggle, the supercomputer. So the challenge is not only in U dou E by dou x, it is there, U dou by dou x plus V dou U. Once we enter the realm of spectral calculations, you are sunk. We do what is called line by line calculation for INSAT 3D and all that. Line by line calculation is the infrared portion of the spectrum. You have to define, you want 0.01 centimeter inverse, that is a wave number, that is the fineness with which you want to do calculations. Therefore, you will have to do millions of calculations, millions of spectral calculations. That is, I want j lambda at let us say 1.00004 micrometer and 1.00041 micrometer, 1.00042 micrometer, 0.00043, then 0.00010, if you want that, then a supercomputer will struggle. Why? Because we are having an instrument which will capture these radiances, then that instrument will have the instrument will behave, it will have a response which varies with wavelength. I have to integrate this using the Planck function, the response of the instrument to this, so that I will know between these two wavelength intervals what is the total energy which is captured or received by the satellite. So if I have thousands of channels on my satellite, which is called a hyperspectral instrument, I will have to do this line by line calculations a million times and then convolve it or integrate it and put it into the various 2000 or 3000 channels, and then I will have to do inverse problem. If this is the reading, what will be the what should be the conditions of the atmosphere which gave this. Okay. So computational radiation is very expensive. Okay. Computational radiation is a craft which is practiced by very few people. Okay. So there is lots of challenges in computational radiation. Okay. Band approximation. Okay, I have epsilon lambda by epsilon lambda versus lambda varies like this. Okay, let the spectral, what is that? Let the spectral hemispherical emissivity of a surface be like this. I want to use a spectral radiosity formulation. I can't use a grey body. It is far from being a grey body. It is having multicolor. It is not a grey body. Now, in the light of what I told you previously, I do not want to do a million calculation, I do not want to do j lambda, write thousands of j lambdas and all that. I want to make the problem tractable. Can you help me out? Is this clear? I want to take one step forward which will simplify this. Come out with something, man. You have learned so much mathematics and make steps, very good. So how do you make the steps? No, I will I don't know, I may do. I don't know whether it will work, but it's okay, I will do something like this. So then I will say this is epsilon 1, epsilon 2, epsilon 3, epsilon 4, and let us say it goes up to infinity. So I can call this as I is equal to 1, j lambda I, I equal to 2, I equal to 3, and so on. What is a major achievement? Instead of integration we can do some summation, all that. Hit the bullseye. What is it mathematically, what have we done to a continuous function? It's a piecewise constant emissivity model. So a continuously varying function has been converted to a piecewise constant emissivity which can be easily handled, and I know I can use the f function chart. Now this sort of epsilon lambda versus lambda, so many problems you have solved, isn't it? Correct? Okay. So the key here to a piecewise constant emissivity model. So piecewise first piece, second piece, so it is a piecewise constant emissivity model. Of course you can have piecewise linearly varying emissivity model, that will be a little more complicated. So when do you think the complexity will increase? You can, as I keep talking, you can note down the points also. The complexity will increase if we employ more bands. Accuracy will also increase as we employ more bands, but it is a trade off between your computational cost and accuracy, right? So accuracy will increase with number of bands, complexity will also increase with number of bands. Accuracy is also critically dependent on how good this piecewise model approximates the non-grey body behavior. That is the final point which I have said is very important. How good this piecewise model, so finally the accuracy of the calculation depends on how good this piecewise constant emissivity model mimics the actual non-gray behavior of the surfaces under question. Okay. Problem number 30, 35.
Sir, this graph is same for all the surfaces in the enclosure.
No, it is. It need not be. If it is same, very good for us.
Then can we just calculate the total hemispherical emissivity and do it with the previous method?
I don't. I think we have to check this. It won't come. What he is saying is every surface has like this. Can we just calculate the hemispherical emissivity once you know the temperature? It will give some answer, but I don't know whether it's 10%, 20%. How far it is off.
No, if they have exactly the same properties, then it will come to
I don't. We will have to do an exercise and find out. Okay. Now problem 35 or 36. 36. Consider two infinite vertical parallel plates. Consider two infinite vertical parallel plates at temperatures T1 equal to 1000 and T2 is equal to 500 Kelvin. Consider two infinite vertical parallel plates at temperatures T1 is equal to 1000 and T2 is equal to 500 Kelvin respectively. The space between the two surfaces is evacuated. The space between the two surfaces is evacuated. The hemispherical spectral emissivity distribution for both the surfaces. The hemispherical spectral emissivity distribution for both the surfaces is given in the figure. The hemispherical spectral distribution of emissivity for both the surfaces for the two surfaces are given in the figure. Compute the net radiation heat transfer from 1. Compute the net radiation heat transfer from surface 1. So I will be decent, I will give a simple so that you do not have. Please take out your F function charts. If you do not have, then share it with your. Okay, 0.7, 0.7, 0.3, 0.3. Okay, so this is epsilon 1 1, this is epsilon 2 2, this is epsilon 2 1, this is epsilon 1 2. That is the nomenclature I am using. Okay, is that correct? First surface first band is 1 1, first surface second band is 1 2, second surface first band is 2 1. Okay, same thing I have made matter simple, it is just mirror image of that 0.7, 0.3, 0.3, 0.7. Beyond 4 micrometer it is proceeding to infinity as a constant value. Okay, first calculate the view factors. Pretty simple, right? I will write the radiosity relations in a using a slightly different nomenclature so that it suits me fine. So I have written the radiosity relation for the ith surface and the kth band, very good. So here I is also varying between 1 and 2, k is also varying between 1 and 2. We will have only 4 equations, 2 sets of equations can be simultaneously solved to get J11 and J21. Second set of equations, are you getting the point? So we can solve for band 1. Then you can add the j's, you can add the q's and get the total q, right, whatever you want. Now better to use the f function charge. How many times you will use this? 4 times, very good, you will use 4 times. Why 4 times? Yeah, correct. 0 to lambda, 0 to lambda and lambda to infinity, okay, 0 to lambda and lambda to infinity for the surface 1 and also for the surface 2, okay. Right, okay. We will first calculate this. Fine, first surface band 1, you got the f, correct, 0.48, then there is no need to calculate this is automatically 1 minus, correct, 1 minus 0.481. I hope everybody is following this. Now I have to do that for the T2 first band. So what is the story there? Lambda max T2 equal to 2000 micrometer Kelvin. Therefore that is f of 0 to 2000, how much is it? 0.061, very good. Now f of 0 to lambda max T2 minus of 2 equal to 0.933, okay. Now we got the important things here, other things are straightforward. Now we will write the bandwise equations. So J11 0.7 to 0.48 to 5.67 10 to the minus 8 to 1000 to the power of 0.3 into view factor. Is that correct? F11 J1 plus F12 J2. Okay. Are you getting this? Correct? So, did you get it? So, J2 dash please check if I made any algebraic errors. That 0.3 into 0.06 and everything is fine. I did it last night, so I have not checked it again. It could be wrong. Huh? Is it fine? Both are fine? Solve for J1, J2. Solve for J1, J2 of 1, that is band 1. Solving the two equations. Any problem with that? 24,000. Abhishek, did you get it? Ramanujam, you got it? 24,000? 428. 24,428 watts per meter square. J2 dash, J21 17,000. Yes, exactly similar procedure. You will get J1 and J2 of band 2. You have got J1 and J2 of band 1, correct? Right. So similarly, see, you had a simple system. Suppose you had 3 surfaces and you had self view factors, it will be very messy. Then you have to do the same thing again and again for how many ever bands you have, plus What do you get on solving this? J12 is it 13,225, that is what I get, check. Okay. So J22 is it okay? Huh? What happened? Equations are right? Huh. Now yeah, get the expressions for J1 and J2. No micrometer, already been integrated. When you use the f function chart, it is already done. How much is it? Yeah, you can get the radiosities, and then Q11 I am able to write Q is equal to J1 minus J2 is because Q is equal to J1 minus G1. G1 for this problem is J2, we have done so many times. When you study for quiz, you should not get confused. How did I write Q equal to J1 minus J2? It is obvious. J1 minus G1. G1 for this problem is F11 J1 plus F12 J2. It is J2. Therefore, I can write. Okay. Now, please fill this. J1 is. Huh? Directly can write, but for the sake of completeness, J1 is 3765. 37650. Yeah, J2 23,282. Yeah, Q1 7428. Q2 Q12 694. So the sum is huh? Yeah, 24,428 is correct or 24,192? Huh? Yeah, so what all will change? This is yeah, then Q1 7191. The total is now 15,000. How much is it? 14,000. 14,000. You can check that Q1 must be equal to minus Q2 because that is the energy balance. Whatever is coming from 1 must go to 2 and vice versa, because there is no other surface which absorbs, emits or participates in the radiation. The view factor is exactly 1 between the two surfaces. Now you got an idea. You can complicate, but I can make epsilon lambda or lambda such that I can give 2-3 places where it is changing, and I can give epsilon for the surface too. I can give some other distribution. So it will be an extremely painful procedure. This is simple.
So if they are not changing at the same lambdas,
Then we can still do. We can. you have to split, and if they are not splitting at the same place, or if I have some, if we want to have fun, then we can do like this. Okay, then it will involved. So you may get stumped for a few minutes, but you can recover and you can proceed. Okay, this gives you an idea of. So I told you that these calculations are important. Don't think it's just of academic interest. When you are working with atmospheric radiation, satellite technology, and all that, all the spectral formulations, there, apart from the spectral formulation, you will have spectral formulation in a participating atmosphere. Okay, that makes it very complicated. Okay.